In this part of chapter, we are going to figure out how to find equilibrium concentrations when given the equilibrium constant and initial concentrations of pressures. There is a plan, strategy, algorithm how to solve the problems when equilibrium concentrations have to be found and when equilibrium constant is given together with initial concentrations of pressures. There are several steps. The first one, we need to decide which direction the reaction will proceed, and this step will be taken when we compare quotient and equilibrium constant. As a second step, we need to define the changes of all reactants and products in terms of x. For this purpose, we need to use coefficients from equation from the stoichiometry and assign positive or negative sign for these changes depends on duration of reaction. And as a third step, we need to solve equation for x. If equation is the second order one, we need to take a square root of both sides or use the quadratic formula. Let us try and apply this algorithm on practice. Let us apply algorithm on this problem. Nitrogen reacts with oxygen, producing nitrogen monoxide, and at some moment of time equilibrium is established in the system. Equilibrium constant is known as 0.10 at 2000 degrees. Initial concentrations of nitrogen and oxygens are provided. We need to find equilibrium concentrations of reactants and products at this temperature. The first step which we need to take is to set up equation for the quotient. And this is the concentration of NO squared, or concentration of nitrogen times equilibrium concentration of oxygen. Let us plug in numbers, and this is not equilibrium concentrations, it's just any concentrations which are provided. So we only know initial concentrations for all these participants. It's 0 at the initial moment of time for nitrogen monoxide, or 0.200 squared, because both initial concentrations are the same, and answer is 0, of course. So now we need to compare quotient and equilibrium constant, and we see that quotient less than equilibrium constant. So what it means, if we apply our graphical method to understand the position of the system versus equilibrium, we will see that quotient, we are on this side, quotient less than equilibrium constant, and changes in concentrations of reactants are negative. Reactants are going to decrease. Hence, when we set up ice table, we have to designate changes in concentrations of reactants with negative sign. Let us create our ice table. Nitrogen, oxygen, nitrogen monoxide. Initial concentrations for both nitrogen and oxygen 0.200 and 0 for nitrogen monoxide. The changes are negative for reactants and positive for product. We don't know how much this change in concentration occurred, but we can say let it be x. Let change in concentration of nitrogen going to be x, and same for oxygen because of stoichiometry, it's a 1-to-1 mole ratio. However, for nitrogen monoxide it's going to be 2x, again due to stoichiometry. Hence, equilibrium concentration for nitrogen will be 0.200 minus x. For oxygen, 0.200 minus x. And for nitrogen, it's a plus 2x. And it's going to be just 2x. Now we're ready to set up expression for equilibrium constant, which is NO squared, concentration of nitrogen times concentration of oxygen, and this time it's going to be equilibrium concentrations. So now just let us put equilibrium expressions for equilibrium concentrations. 2x squared over 0.200 minus x squared. I can square it because equilibrium concentrations for nitrogen and oxygen are the same. Well, and we know that equilibrium concentration is 0.10 at this particular temperature. The only what we need to do is just to solve this for x. Let us rewrite this expression. Equals 0.10. And now chemistry is over. We need to solve this for x. And there are two ways how to do this. We can solve quadratic equation, or we can get rid of square. Let us simplify it. Let us take square root from both sides, and it's going to be step by step. Of course, make an assumption that 0.200 is not equal to x. Okay. We took this, and then we have 2x over 0.200 minus x equal 0.316. When you solve this, x is going to be 0.027. What is that? This is change in concentration of nitrogen and change in concentration of oxygen. They are the same due to initial concentrations are the same, and stoichiometry is 1 to 1, 0.027. And now we need to find equilibrium concentrations for nitrogen and for oxygen, and it's going to be again the same for both, and we usually designate equilibrium concentrations with asterisks. 0.200 minus 0.027 equal 0.173 molarity. Okay, and equilibrium concentration for nitrogen monoxide is 2x, hence this is 2 times 0.027 equal 0.054 molarity. And the very last step, let us check our calculated equilibrium constant versus given equilibrium constant, and it's going to be 0.054 squared over 0.173 squared. The answer is we need to take a calculator and calculate it. 0.054 squared divided by And the answer is 0.097, which is close enough to the given 0.10, which means our calculations are valid and problem is solved. Let us try another problem. This time we have reaction between dinitrogen tetroxide and nitrogen dioxide. At some moment of time, equilibrium is established, and equilibrium constant is known as 0.36 at 100 degrees Celsius. Also, we knew initial concentrations of nitrogen dioxide, and we don't know anything about initial concentration of dinitrogen tetroxide. If nothing is provided, no information about initial concentration of dinitrogen tetroxide, hence we can make an assumption it was a 0. Well, so same step, we need to start with quotient. Expression for quotient is NO2 squared over concentration of N2O4, and it's going to be 0.100 squared. Initial concentration of dinitrogen tetroxide is 0, and we know that division by 0 gives us infinite. So quotient in this case greater than equilibrium constant. Our graphical method gives us hint that we are on this side of our diagram, and equilibrium constant smaller than quotient. It means reaction will proceed backward, and concentrations of products will decrease this time, and we have two products. And when we set up our ice table, we need to designate changes in concentrations of products with negative sign. Let us set up this ice table. So dinitrogen tetroxide and nitrogen dioxide. Initial concentration of dinitrogen tetroxide 0. Initial concentration of nitrogen dioxide is 0.100. And now, like we said, changes in concentrations of reactant are going to be positive, and changes in concentration of product are going to be negative. Why so? Because quotient is greater than Kc, and reaction proceeds in backward direction. Okay, do you know magnitude of these changes? No. This is why we have to assign it with x. Usually, the most convenient to let x represent the change in concentration of the reactant or product with, attention, the smallest stoichiometric coefficient. The smallest stoichiometric coefficient in this example is 1, and this is for dinitrogen tetroxide. This is why let us put x for changes in concentration for dinitrogen tetroxide. Hence, by stoichiometry, it's going to be negative 2x for nitrogen dioxide. Then equilibrium concentration for dinitrogen tetroxide is going to be x, and equilibrium concentration for nitrogen dioxide is going to be 0.100 minus 2x. Now, let us set up expression for equilibrium constant, and it's NO2 squared over N2O4 equal 0.100 minus 2x squared over x, and this all is equal to 0.36. Now we need to solve this equation for x. Let us rewrite this expression. 0.100 minus 2x squared over x equal 0.36. Now chemistry is over and we just need to solve this equation. Looking at this equation, we understand that this time we cannot take square root from both sides. So hence we cannot get rid of quadratic equation. Hence, are you ready to solve quadratic equation? We have to. Let us do this. So first of all, let us simplify this equation. 0.100 minus 2x squared equal 0.36x. I just multiply both sides by x. And now I need to open their parentheses, and it's going to be 0.0100 minus 4x plus 4x squared equal 0.36x. Then let us rearrange it. 4x squared minus this 0.4x minus 0.76x plus 0.0100 equal 0. Well, right now we ready to solve quadratic equation, and let us set up formula for quadratic equation. I'm going to use another color. So x for both roots will be found by this formula: minus b plus minus square root of b squared minus 4 times a times c over 2a. Let us set up what is our a, what is our b, and what is our c. A is 4, b is negative 0.76, and c is 0.0100. Okay, just let us plug in number in the formula and find x 1 and 2. Okay, it's going to be x 1 and 2. So far we can solve them together. Going to be minus 0.76 plus minus square root 0.76 minus 0.76 squared minus 4 times 0.0100 over 2 times 4. Okay, now let us continue on this side. X first and second will be 0.76 plus minus 0.65. This is result under the square root over 8. And now we can separate them. 1x, the first root is going to be 0.176, and x2 is going to be 0.014. Let us analyze these results. The first root of this equation has to be rejected because the result is greater than initial concentration, which was provided in the formula. As far as reaction proceeds in backward, hence equilibrium concentration cannot exceed initial concentration. This is why the first root can be accepted. We have to exclude it. We reject this root. So the only root which we need to accept is the second one. And now let us continue with this answer. So let us finally find the concentration of NO2. Equilibrium concentration is going to be 0.100 minus 2x, which is 0.100 minus 2 times 0.014, and it equals 0.072 milliliters. And concentration for dinitrogen tetroxide at equilibrium is X molarity. The last step, which is also we need to take as expression for equilibrium constant and check how it matches to equilibrium constant provided in this problem. Divide by 0.14, and the answer is 0.37, which is good enough and matches enough to the original information, original equilibrium constant provided in this problem. Answer is valid. Problem is solved. We remember that when equilibrium is established, we usually have in our reaction mixture both reactants and products. However, when equilibrium constant is very small, it means that position of equilibrium favors the reactants, and the most are reactants in the reaction mixture. If together with this we have relatively large initial concentrations of reactants, then we can make an assumption that the change in concentration of reactant will not be significant, and we can say that equilibrium concentration of reactants is roughly the same as initial concentration of reactants. Of course, if we know that reaction proceeds forward. One more time, when we can make this approximation, if equilibrium constant is very small and initial concentrations are large. Of course, any approximation has to be checked and validated. So the valid approximation is assumed to be when value of x is less than 5% of the initial concentration. Let us try new problem. So this time we are given reaction between dihydrogen sulfide and hydrogen and sulfide. Equilibrium is established in this mixture. Equilibrium constant is 167 times 10 to the power negative 7 at 800 degrees Celsius. Equilibrium constant is a very small one. Want to bring your attention? Then a 0.500 liter reaction vessel initially contains 0.0125 moles of hydrogen sulfide. We need to find equilibrium concentrations of hydrogen and sulfide. Okay, first of all, we need to find concentrations because ice table includes only concentrations. Okay, let us find it. So the concentration of hydrogen sulfide is going to be 0.0125 mole over 0.500 liters, and this is 0.0250 milliliters. Okay, excellent. The second step which we need to take is to figure out the quotient and how it's related to equilibrium constant. Okay, expression for quotient is hydrogen squared times sulfur over concentration of hydrogen sulfide squared. Now let us plug in numbers. We have 0 concentration for hydrogen, 0 for sulfur, and 0.0250 we just calculated for hydrogen sulfide, so quotient is 0. Hence, in spite of equilibrium constant is a very small one, quotient is still less than K. Hence, reaction proceeds forward. Reaction proceeds forward. Reaction proceeds forward. It's important to understand because when we set up our ice table, concentrations of reactants are going to decrease. We have to assign them with negative sign. Okay, H2S, hydrogen, and sulfur. So initial concentration of hydrogen sulfide is 0.0250 for hydrogen and sulfur zeros. Now we need to assign signs, negative for hydrogen sulfide and positive for hydrogen and sulfur. Now let us designate change in concentrations as X for sulfur, because this time this change will be represented by X for product with the smallest coefficient, stoichiometric coefficient in the reaction. Hence, by stoichiometry it's going to be 2x for hydrogen and 2x for hydrogen sulfide. Then equilibrium concentrations will be 0.0250 minus 2x, 2x for hydrogen and x for sulfur. Excellent. Now let us set up expression for equilibrium constant, and this is hydrogen squared times sulfur over hydrogen sulfide squared, and then let us plug in expressions for equilibrium concentrations, and it's going to be 2x squared times x over 0.0250 minus 2x squared. Okay, let us simplify it. 4x cubed over 0.0250 minus 2x squared equal 1.67 times 10 to the power negative 7. This equation has to be solved for x. Okay, let us rewrite this expression again. 4x cubed over 0.0250 minus 2x squared equal 1.67 times 10 to the power negative 7. Okay, so the chemistry is over. Now we need to analyze this expression, and it's time to make some assumption, because we are, in other case, we need to solve cubic equation. Well, let us apply our assumption. The equilibrium constant is relatively small one versus relatively large initial concentration. Hence, we can make an assumption that x is small. So it means the change in initial concentration will not be significant, and we can say that the change in initial concentration x can be assumed as a 0. Okay, if so, what we will have? We will have 4x cubed for our example over 0.0250 squared equal 1.67 times 10 to the power negative 7. Now this equation is much easier than the previous one. Now we can solve it. Okay, let us do some simplification. 4x cubed equal 167 times 10 to the power negative 7 times 0.0250 squared, then x cubed equal 1.67 times 10 to the power negative 7 times 0.0250 cubed over 4, and x is 2.97 times 10 to the power negative 4. Let us do approximation check. Approximation check. So, and it's going to be 2.97 times 10 to the power negative 4 divided by initial concentration 0.025 times 100%, and this is 1.19%, which is less than 5% assumption. Hence, our assumption is valid. Okay, excellent. Now Our next step is to solve our equation for x. Now we need to substitute our x in original equation. So what we will have? 4x cubed over 0.0250 minus 2 times 2.97 times 10 to the power negative 4, everything squared, equal 1.67 times 10 to the power negative 7. Okay, so when we solve it, we will get x equal 2.92 times 10 to the power negative 4. And this result is nearly identical to which we got during our approximation, times 10 to the power negative 4. Therefore, it's a good approximation. Then we just need to continue and finish this problem with the concentration, the change in concentration which we got, and then just the last step. The equilibrium concentration of hydrogen sulfide is going to be 0.025 minus 2 times 2.97 10 to the power negative 4 equal 0.0244 molarity. Equilibrium concentration of hydrogen is 2 times 2.97 times 10 to the power negative 4, which is 594 times, let me rewrite it and make it more accurate. So this is 5.94 times 10 to the power negative 4 molarity, and concentration of sulfur is 2.97 times 10 to the power negative 4 molarity. And now is just the very last step. We just need to calculate equilibrium constant with found equilibrium concentrations and validate our solution. So it's going to be 5.94 times 10 to the power negative 4, and this is squared, times 2.97 times 10 to the power negative 4 over 0.0244 squared, and answer is 1.76 times 10 to the power negative 7th. So the calculated value of K, this is our calculated, is close enough close enough to the given one, which is 1.67 times 10 to the power negative 7. And therefore the answer is valid.